let's take the shielding tensor. The shielding tensor. Let's take the alpha beta component of the shielding, and that was, let's jump back to our definition which we had on Tuesday. We had that defined as the derivative of the energy, second derivative of the energy with respect to an alpha component of the magnetic moment and the beta component of the field, magnetic field. So now we have with magnetic properties deal with, and we have to find all the terms which depend on those. So this is going to be something with a magnetic moment. So it would have in principle that, that, and that, and one with a B field, that's this one. And then quadratic terms, it's this so-called bilinear. So now we have a derivative of we have one of those, and that is immediately going to be this one. And I mean the argument is still the same, that if I take the second derivative, because the wave function here in the second order energy correction are unperturbed, so I just get the derivative of the operator. So I get psi 0, and then well, I get this P ds A, and I get the alpha beta component of that, psi 0. And then I come to my second order energy correction. And I have to, in principle, in the first order Hamiltonian, I have all that standing in here. But I mean, the situation I'm looking at is where I have a B field and a nuclear magnetic moment present. And I evaluate the derivative afterwards for 0 external magnetic field and for 0 nuclear magnetic moment. So I only have those terms to think of. And then I really end up in the same situation as here. I get those terms, so let's try to do that. So plus, and let's take first the derivative with respect to a B field. So I keep the derivative with respect to the magnetic moment, the alpha component of the magnetic moment. I get a sum over n. The numerator is always the same. No, denominator is always the same. And then I get psi 0. And I take the derivative with respect to the magnetic field now. So I'm going to get this operator in there. That's the only one which has a magnetic field here. So I get pi p1 c and what do I say, beta psi n. And then the second one I keep as it is, psi n, and let's keep our first order Hamiltonian, psi 0, plus, I'll just put it on a big ratio. I take the derivative of the second one, psi 0, Hamiltonian 1, psi n, psi n, and again psi 0. And then I have to take the second derivative, PA diamagnetic shielding, alpha beta component, psi 0, where I now can take the derivative in this part. So I get sum over n is 0 minus En psi 0 P1 beta C psi n and then I would get this one PSO PSO A alpha. I would get this one and that one. Now remember both operators here from half an hour ago. They both included the electronic spin operator. So I would get terms in here which have the electronic spin operator. Now if the electronic spin operator acts on a wave function, that is going to change the spin of the wave function. Remember, if x and y I can write up as plus and minus combination, s plus and s minus, and s plus and s minus increase the ms value. So, and I have to do a spin, I integrate over spin afterwards. If I have now an electron spin operator here and I start with a closed shell singlet state here, if I let the spin operator act on that, this is going to become a triplet state. And the rest of the operator has no spin in there. So if I do a spin integration, I only get something if this is a triplet state. But this state is the same as this state. So if this is a triplet state, has to be a triplet state, this is the same triplet state. But here I have an operator which includes no spin. So then for this integral, this transition moment to be different from 0, psi 0 had to be a triplet state. But I started out with a singlet. Which means in this sum over states expression, I can have spin operator, electronic spin operators in there, but I have to have them either in both or not at all. If I only have them in one, then I'm going to get 0 because, coming from here, this is singlet, doesn't change the spin, this has to be singlet. Coming from there, singlet, spin operator, this has to be triplet, and the same state cannot be a singlet and triplet at the same time. Which means here where I have this operator on one side, which is a purely spatial operator, I can't have those two. In principle they should be there, but the integrals over them are 0. So the only one which really is there is this PSO term. And then, don't want to write it up, I get the complex conjugate, I get them in a different order also.